Hello and welcome to the fourth part of Lesson 7. We've spent the last lesson and a half solving the energy equation for a variety of different scenarios. We've looked at steady state and transient problems, problems that can be assumed to involve one-dimensional conduction heat transfer, and those where conduction is in two dimensions. We've also examined problems that involve convective heat transfer to or from a surface, advection of heat in moving materials or flows, and also briefly discussed radiative heat transfer. The only thing that we haven't done to date is to examine phenomena that can lead to a volumetric energy source being present. That is what I'd like to cover in this part of this lesson. And I'd like to do it in the context of something that is very relevant to the flows of highly viscous liquids in small gaps, and that is frictional heating. Now, when I say frictional heating, the first thing that might pop into mind is something akin to what I've put on the board there, rubbing two sticks together to get fire. We can do this. It's a heck of a skill. The best way to rub two sticks together is actually to rotate one stick in a little sort of divot in another to get some warm coals from that, some very, very fine charcoal from that hopefully with some dry tinder and sufficient application of blowing will get a small flame which can then grow and grow and grow and eventually, and after much trouble, get a larger fire going. But we can directly relate this phenomenon to something that happens in the flow of highly viscous liquids. So the scenario that I'm talking about is, for example, the flow of a molten polymer where the zero shear viscosity might be tens of thousands of pascals second, and we're looking at how that polymer deforms in the flow. And an idealized cartoon of how that polymer deforms in the flow is to imagine layers of polymer slipping over one another, creating internal friction, creating a source of energy loss, creating heat. And so what one finds is if you've got flows of highly viscous liquids through quite small geometries, capillaries or extrusion dyes where you've got very, very fine details present, you're going to get viscous dissipation. And this can be a big problem because viscous dissipation generates heat, and heat changes the physical properties, particularly the viscosity of the material that we're looking at. So we need to be aware of this phenomenon. So viscous heating is sometimes termed internal friction. From the standpoint of the energy equation, it appears as an energy source term. So let's think of it from that standpoint first. There on the board is my energy equation, and in red there is the energy source term, that term that we've up until now pretty much set to zero. If we're including viscous dissipation, we include the term tau, the stress due to deformation, double dot product, grad V, the velocity gradient tensor. And you might at first sight saying, well, hang on a minute. Whenever we look at an equation, we always look at the units and understand it. We know that the energy transport equation as written on the board has units of watt per meter cubed. It's a volumetric rate of energy transfer. But the units of stress are Pascal, and the units of velocity gradient are meters per second over meters, which is 1 over second. So that viscous dissipation term has units of Pascal over second. How is that consistent with watt per meter cubed? Well, I'd invite you to think about that, because what is Pascal? It's a Newton per meter squared. Okay, let's multiply top and bottom of Newton per meter squared by meters. That gives us Newton meters per meter cubed. So the denominator's got the meters cubed bit in of the energy transport equation. So that leaves us here Newton meters over seconds. Well, what's a Newton times a meter? What's a force times the distance? It's work done, joules. So you've got joules over second, which is watts. And so Pascal divided by second is indeed dimensionally correct in terms of it being in watts per meter cubed. So we can quite validly incorporate tau double dot product grad V as the energy source term due to viscous dissipation. We can simplify that one step further, because if we're going to make an assumption of maybe flow is going to be described in a generalized Newtonian manner, tau is going to be eta, my non-Newtonian viscosity, my generalized Newtonian viscosity, could be Corot, could be power law, times gamma dot, my rate of strain tensor. Okay, so there we have internal friction or viscous dissipation included in the energy transport equation, and we'll look at that double dot product in a little bit of detail in a second. So let's look at the complicating factor here. We've got a number of physical properties in the energy transport equation. We've got viscosity, we've got density, we've got heat capacity, we've got thermal conductivity, all of which are functions of temperature. Right, so the term that generates the energy source is pre-multiplied by viscosity. And that term only becomes relevant at high viscosity, but as we generate heat, typically viscosity will drop. And so we've actually got a very, very coupled equation here where we need to be able to describe the temperature dependence of viscosity accurately in order to solve viscous dissipation within the energy transport equation. Okay, so that's a ramification from a theoretical and a numerical standpoint. I want to look at the pragmatic standpoints now, and I'm going to start by saying two words: capillary rheometry. If you're doing capillary rheometry of viscous liquids, what are you doing? You are flowing a highly viscous liquid, typically, especially if you're dealing with a polymer melt, through very narrow geometries at incredibly high shear rate. Why are you doing this? You're doing it to measure a pressure drop so that you can measure the viscosity of a material. We're assuming, in doing that it's isothermal. It might not be. Viscous dissipation can be a major source of error if you're measuring the viscosity of materials using rheometry at high shear. Capillary rheometry is one high shear technique, but equally we can generate pretty high shear rates in rotational tools as well, and again, viscous dissipation may be an error source in the data that you're obtaining, especially if you're dealing with materials that are polymer melts that have a very high zero shear rate viscosity. So please be aware of this. One of the ways in which we can judge whether viscous dissipation is a problem or not is by use of a non-dimensional group. We need to be aware of this in experimental measurements. We need to be aware in calculation work of whether or not to include viscous dissipation. And if we do, we need to do it with some care, and it's probably going to be a numerical result, and we've got to couple all the physical properties of temperature, and the term that generates the energy is coupled to viscosity, which is coupled to temperature, and so it becomes a solution that requires a little effort to obtain in the first place. So if we don't actually need to include the effect and go to that level of trouble, then we'd quite like not to. So the judge that we can use is the Narmer-Griffith number. Now, the Narmer-Griffith number is a measurement of the effect of temperature on viscosity. So let's run through the parameters that it involves. Eta 0 is my reference viscosity. It might be a zero shear rate viscosity, it might be a reference viscosity. And we are looking at the temperature dependence of that reference viscosity. Talk about that in a second. V here is a characteristic velocity of the system. K is my thermal conductivity. Beta is the temperature sensitivity of the viscosity. So let's have a look at that viscosity now. So let's say my viscosity is being modelled as a function of temperature as an exponential change. Eta equals eta 0 exponential of beta t minus t0. That's where beta features. It's the form of that exponential variation. And what we find is that if the Narmer-Griffith number falls between 0 and 0.5, then we can assume that viscosity is unaffected by temperature, which is a very, very useful result. If it's greater than 0.5, yeah, well, we may well need to incorporate the effects of viscous dissipation. Okay, so if we're incorporating viscous dissipation in the energy equation, then we need to be able to simplify its formulation effectively. So let me remind you what the double dot product looks like. I'm going to do this in Cartesian coordinates for simplicity, and I'm going to write out both tensors in full, just so you can see what they look like. There's gamma dot, my rate of strain tensor, and we've seen this a number of times in previous lessons. The tensor in purple on the right hand side is grad V, and remember it's grad V makes up one of the components of the rate of strain tensor in the first place. The double dot product is simply we are taking the product of every row-based element in the first tensor with every column-based element in the second tensor. And so we end up with a result that looks as follows. So it's scalar result, which we would expect because the energy transport equation has terms that are scalar being added together, and so we expect a scalar result. Also, it's a result that we can simplify greatly just by thinking about the problem, just as we've been doing on our workflow to solve energy transport problems. So we'll always simplify this problem before we use it. So let's say, for example, we've got a simple shear flow where in Cartesian coordinates we've got an x direction velocity that simply changes in y. There's no y direction velocity, there's no z direction velocity. Then the only term that remains of this double dot product is simply dvx by dy all squared. And that's nice and easy to deal with. And we'll see how we can use this in the final part of this lesson. So let's recap a few key points. Flows that have a very high viscosity fluid involved can be prone to internal friction, otherwise known as viscous dissipation. The heat generation by viscous dissipation is proportional typically to the square of the magnitude of the shear rate in simple shear flow. So heating will happen in zones of high shear, that is to say near a wall or a no-slip boundary. The heat generation is also proportional to the viscosity of the material, but don't forget the viscosity is proportional to temperature. So if we're solving the energy transport equation to include viscous dissipation, we need to be highly aware that we've got a very, very coupled problem to solve, which impacts on how we do this numerically. If we want to judge whether or not to include viscous dissipation, the Namus-Griffith number is the go-to non-dimensional group to use. If it's between 0 and 0.5, we can neglect viscous dissipation. If it's above 0.5, we're going to have to incorporate it. The final note is be aware of viscous dissipation when you're taking measurements of material properties, specifically in any rheometry that involves high shear.